Hello, and welcome to the VERA Basic Use tutorial video. The Versatile Electrode Localization Framework, VERA, is a MATLAB-based tool that was built to simplify the process of localizing ECOG and SEEG electrodes in the MRI coordinate space. This is a crucial step in invasive neurophysiology research, as precise knowledge of the recording locations is critical to interpreting electrophysiological recordings. If you have not yet installed VERA and the necessary dependencies, please make sure to watch our installation tutorial video first. VERA is an extremely useful tool for reducing the tedium of localizing electrodes manually, with existing integration of a variety of co-registration tools and support for partially automated electrode localization. However, VERA aims to go beyond this, acting as a modular and extendable framework for integrating other tools seamlessly into a processing pipeline, such as introducing a new functional atlas for labeling electrode locations. The result is a profile of a subject capturing all of the details of the electrode localization in one place, along with the results of each processing step in the localization pipeline, ensuring no information can be lost. A MATLAB data structure packaging the segmented brain model, electrode locations, and labels for many atlases used in the processing pipeline can also be produced for further analysis. In this video, we will talk through the VERA GUI and how VERA assembles different components into pipelines. Launch VERA using the Startup VERA M file located in the VERA project folder. Create a new project by navigating a File, New Project. Select a folder in which you want to create the new project. I usually create a new folder to store the project in. After you select this folder, a dialog box will open asking you to select a pipeline to use for this project. For the basic use tutorial, we will select the simple tutorial pipeline. You should see that VERA has populated the new project with the pipeline components on the left side and the views along the top. Click the drop-down arrows to expand the input, processing, and output fields of the pipeline. Let's talk about this pipeline in some detail before moving on. Pipelines are text files written in HTML that describe which components will be used for a project. Pipelines are broken into input, processing, and output components. Input components do not rely on details from other components the way processing and output components do. The four input components in this simple tutorial pipeline are the electrode definition, a CT loader, an MRI loader, and a FreeSurfer surface loader. The electrode definition includes details about the implanted electrodes, including the type of implanted electrode, electrode names, number of electrodes on each implant, inter-electrode spacing, and electrode volume. The CT and MRI loader components can load DICOM or NIfTY files into VERA to allow for co-registration later. Finally, the FreeSurfer surface loader component loads the FreeSurfer segmentation surface. If you have not already generated the FreeSurfer segmentation, you can replace this with a FreeSurfer model generation component in the pipeline file. We'll talk about this more in the VERA extended use tutorial video. Processing components manipulate VERA data in meaningful ways, and therefore rely on input components. The processing components in the simple tutorial pipeline include move RAS origin, co-registration, MATLAB electrode selection, FreeSurfer electrode selection, and reorder electrodes. The move RAS origin component works in conjunction with the co-registration component. This simply ensures that the CT and MRI images are overlapping enough to be successfully co-registered. The co-registration component uses SPM12 to co-register the CT to the MRI for precise electrode localization in the MRI coordinate space. The MATLAB electrode selection component is a semi-automated electrode localization step that thresholds the CT and uses the electrode definitions to identify the electrode locations using a maximum likelihood estimation approach. This can be used to manually or semi-automatically identify SEEG and ECOG electrode locations. The results of this component must be manually verified in Freeview using the FreeSurfer electrode localization component. The FreeSurfer electrode localization component opens Freeview and loads the CT and electrode locations to verify that the locations are correct and make any necessary changes. Finally, the reorder electrodes component automatically reorders the electrode numbering to count from the distal to proximal ends of the electrodes. If this step fails, there is also a GUI to fix the electrode ordering manually. Lastly, output components store some data outside of the VERA project. In this simple tutorial pipeline, we have included a MAT output component and the report generator. This MAT output component stores the brain surface and electrode coordinates to a MAT file to be used outside of VERA. The report generator component utilizes another tool developed in our lab called the report generator to generate a PowerPoint report of the implant locations and a slice view showing the location of each electrode in the coronal, sagittal, and horizontal sections of the MRI. Currently, we can see that there is a red X next to each component. This means that the component has not yet been configured. VERA requires a component configuration step to check that the internal dependencies, such as a CT loader input component for the co-registration component, and external dependencies, such as the path to FreeSurfer for the FreeSurfer electrode localization component, can be found. Right-click on a component to configure it, or click on the Configuration drop-down menu and select Configure All Components. The red X's have now changed to yellow checkmarks and yellow wrenches. The yellow checkmark indicates that the component is configured and ready to be run, while the yellow wrench indicates that the component is configured but still requires some precursor component to be run before it is ready. Once a component is finished running, a green checkmark will appear. If you are seeing some warnings about non-existent paths, or error messages that VERA is unable to open a file, check the configuration settings to make sure all of the dependency paths are set correctly. There's more information about this in the installation tutorial video. After a component is configured, you can double-click it to run. First, we will create the electrode definition. This is typically provided by the neurology team. Add electrodes using the Add button. The number of electrodes per implant, inter-electrode spacing, and electrode volume are used for the automated electrode localization. SEEG electrodes typically have a volume of about 30 cubic millimeters. Populate this table with the electrode definition information. close this window to store the electrode definition. Run the CT loader by double-clicking. Navigate to the folder where the subject's CT is stored and select one of the files. If it is a DICOM file, VERA will take the path to this file and load all other files automatically. Navigating to the slice view will reveal that the CT has been loaded. You can look through the slices using the slider bars, as well as adjust the contrast and opacity of the image. You can load the MRI files in the same way as the CT. We can now see that the MRI has been loaded, but is clearly not co-registered with the CT. Finally, load the FreeSurfer surface by selecting the subject's segmentation folder. Again, we'll discuss generating the segmentation in the VERA extended use tutorial video if needed. Navigating to the 3D view will show that the surface model has been loaded with the Desikan-Kiliani atlas as the default. Run the Move RAS origin component to bring the CT to the origin of the MRI volume and improve the chance of co-registration success. VERA uses SPM12 to co-register the CT to the MRI. Adjust the opacity of the top image to check if the co-registration was successful. It's important to always check if the co-registration succeeds. The MATLAB Electrode Selection tool can be used to speed up the process of identifying the electrode locations. Although it often does a good job of identifying most of the electrodes, it will almost always miss some. Therefore, the goal of this step is not to identify the location of every electrode, but only to make progress towards identifying all of the electrode locations. In the next step, we will open Freeview and manually verify the location of every electrode. The MATLAB Electrode Selection tool is usually used with a picture detailing the implant plan if no other information about the trajectories is available, such as from ROSA. I usually start by orienting the brain I want using the Orbit Camera tool. You can also adjust the opacity of the brain model using the slider at the bottom of the window. You can also adjust the thresholding of the CT using the top slider at the bottom of the window. This is changing the density threshold for the CT in an attempt to resolve the correct number of electrodes. The left side of this window lists the electrodes defined in the electrode definition step. You can designate an electrode as part of the highlighted implant by clicking on it. Make sure to turn off the Orbit Camera tool to select electrodes. Select each point that belongs to the implant. Once you have found as many electrodes as possible, close this window. We will manually finalize the electrode localization in the next step. Looking at the 3D view, you should be able to adjust the opacity of the brain model to see the identified electrodes. The FreeSurfer electrode localization step tends to take the longest and is also the most crucial. Using the FreeSurfer electrode localization component, we will open Freeview to manually check the electrode localization performed in MATLAB and correct any mistakes that have been made. At the end of this step, the number of electrodes in each implant has to match the number expected from the electrode definition. Note that if you are using VERA on Windows, you will need to start up Xlaunch with native OpenGL disabled to use Freeview. I typically first show the CT as an isosurface in the 3D view to better compare the electrode coordinates to the CT. This can be found at the bottom of the left panel when the CT volume is selected. Set the high threshold to the maximum and the low threshold to about 2000 for the best results. Next, I select all of the point sets and increase the radius to 2 and uncheck the Snap to Voxel Center. Navigate through the slices using the Navigate tool to see the identified electrodes. At this point, we will start working our way through the electrode list to ensure that the correct number of electrodes have been localized and that their locations align well with the CT. I usually change the color of the electrode I'm focusing on to red, and then use the Go To tool to navigate to the first electrode. To add or edit a point, use the Point Set Edit tool and left-click on the slice view to place a point. Points can be moved by left-clicking and dragging, or removed with Shift-click. Try to align the points with the densest parts of the CT in the slice view. Often, it is necessary to adjust a point's location in all 3 slices to ensure it is placed accurately. Sometimes, electrodes are not implanted to their full depth, and some contacts are still inside of the bolt. I do my best to approximate the location of these electrodes anyway, with a plan to exclude them later in post-processing, because VERA is expecting the number of electrodes defined in the electrode definition. Save each electrode as you go to avoid losing progress. Once you have finished placing all of the electrodes, double-check against your electrode definitions to make sure you have the correct number of electrodes for each implant, and make sure each implant is saved. Close Freeview. If you have an error saying you do not have the correct number of electrodes for an implant, run the FreeSurfer electrode localization component again to correct your mistake. Be sure to select Keep All to keep the work you did the last time you ran this component. Selecting Override All will override the results from the last run of the FreeSurfer electrode localization component with the results of the MATLAB's electrode selection component. The last step of this simple tutorial pipeline is to fix the electrode numbering. Implanted electrodes are typically numbered from distal to proximal. Again, you can rotate the brain model using the orbit camera tool to see if the electrodes are numbered properly. If they are not, use the Resort Indices button to manually set the electrode numbering. Alternately, you can use the Auto Sort button to attempt to number the electrodes from the center of the brain out. This does not always work correctly, so be sure to double-check the result. Lastly, you can select all implants in the list to auto-sort them all at once. Again, double-check the numbering of each implant to ensure that it is correct. When you are finished, hit Accept. You should now be able to see all of the identified electrode locations in the 3D view. Next, we will output a data structure to access the brain surface and electrode location information outside of VERA, and generate a report of the electrode locations in PowerPoint. Running the createbrain.mat component opens a dialog window to save a MATLAB mat file containing the brain model and electrode locations. The data structure saved by VERA stores several useful fields, including the cortex, which contains the brain surface model, the annotation, which contains the surface labels, the electrode names, which contains the names of every implanted electrode, the TALA structure, which contains the three-dimensional electrode coordinates, as well as some legacy variables, and the secondary label, which contains labels for each electrode's implanted location. Finally, the last step in the simple tutorial pipeline is to generate a report of the electrode locations using the report generator component. This report shows the location of each electrode in the 3 slice views, and is helpful as an easy overview of the electrode locations. Note that the report generator tool creates screenshots of each electrode location and stores them in a PowerPoint file, so a licensed version of PowerPoint is required to use it. Running the report generator component opens an external tool. In the report generator tool, you can view the localized electrodes in the slice view and change various imaging options. You can also plot the surface to show the location of implanted ECOG electrodes or the SEEG trajectory. I usually start by navigating to the Imaging Options tab and using a yellow dot for the electrodes. I also turn on the 3D model. On the Grid Options tab, you can specify whether the implanted electrodes are ECOG or SEEG electrodes. In this example project, all of the implanted electrodes are SEEG electrodes. Click Apply Changes to set the grid options. You can now see that the SEEG trajectories are shown on the 3D model. Click Proceed and Generate Report and enter a report name. When the report is finished generating, select a name and location to store the report. This is the end of the simple tutorial pipeline, and is the minimum amount required to identify the electrode locations in MRI space. In the next video, we will talk about extensions to this pipeline, including adding ROSA trajectory planning information to make electrode identification even easier, introducing subcortical segmentation via FreeSurfer to improve the quality of the electrode labeling, such as labeling an electrode as CA4 instead of hippocampus, and transforming electrode coordinates into MNI space. Thank you for watching our video.